I just kept my mask because it's an advertisement to the place where I'm here now, because I'm the director of a French lab, French CEMRACS lab, inside a foreign country, which is Canada. And if I would be correct, it would be to say if it's in Quebec. And the CNRS has plenty of labs in every field all over the globe. And every French researcher which is in the Ministry of Superior Education can apply for a position of 6 months, 1 year, or more in any other institute to work with colleagues abroad. And the CRM is one of them. It's a center which is 50 years old and which organizes thematic semesters on every field in pure, mostly, and applied mathematics. And it's also a lab where Joshua Benjo, who got the Turing Prize, is at the head of Mila. And so my talk of today, I decided, even if I have slides, to present on board, because I think that for a workshop, it's important that you can follow at the speed at which I write and not at the speed at which I can go through slides. So the two models, the first one, I will be quite dubious on the presentation because it's works I've done 20 years ago. So I had to refresh my memory on all the proofs. So to tell you that it's normal to forget when you do something. And that's very common when you look at a paper that you wrote. Oh, how did I prove that? And why this is true anymore? And so, and the second one is an ongoing project. The two projects are linked with things I've done when I was at the French Atomic Energy Commission. The first one was a problem of porous media, and the porous medium problem for the CEA is important because you have to deal with the fact of nuclear waste. And if you want to put nuclear waste in a safe place, you have to know if in the next 100,000 years there might be some water coming into the concrete and so damaging the thing which is around the nuclear waste. So you have to look at the exact behavior of porous media in any constraint. So that was the thing which led me first to understand that rather than having extremely precise codes for solving extremely precise problems, when we are on a multiphysics problem, it's very hard to couple the codes themselves because you have sometimes some enhancement of properties given by the coupling of the models because you have more richness of the global model than in each model. And the first one will be on porous media. When you know that a porous media, it's a parabolic degenerate problem because when the medium is full of water, the quantity of water in the medium doesn't grow anymore. So that means that the PDE that is considered for this problem will be degenerate in the time term. So that is the first problem. And the second problem is a problem which is an ongoing project with many colleagues, including Stéphane Delacherie, with whom I worked with that from 10 years ago about for coupling the neutronics equation for computing the density of neutron inside a nuclear core and the thermohydraulic equations. And you will see a very funny cartoon I will draw on the board for how things were done till 5 years ago. So I began that with Stéphane Delacherie, then with Erel Jamelot, and now with François Madiot, who is here, with François Dubois at Le CNAM, who was at Montréal this year And we worked on this project, and numerous students, among them Riaz Muhammad, Abdel Koudous Moussa, and this year Martin Duguay. Two of them were from the engineering school in Applied Maths of Paris 13, LAMAX, and the last one was in Central Casablanca. That's where I met with them. So let's go to mathematics and problems. So the first equation will be the porous media equation. So we have two laws to take into account. We have a very famous Darcy law, which is also called sometimes Fick's law, and that gives the velocity of a fluid, inside a porous medium, which is a quantity, which is the porosity omega, of the medium, in fact, it's the volume of the empty pores divided by the total volume, and omega times coefficients that I will write under this form only. E is the height of the column of water, mu is the viscosity, and of course, it's generated by the second equation of the earlier equations, where h is the height, equivalent height of water, and z is the altitude. And so this law, it's written as a function k star, which depends on omega, which is the porosity, as I said, the pressure of water times gradient of h, where h is the height of water. So that's the first equation. The second equation now is the equation which gives the conservation of the mass. And it writes dt of rho theta plus divergence of rho u is equal to, let's say, minus rho q, where q is the inflow of water. Theta is the quantity of water which is in the porous medium, which is closely related to omega. It's essentially theta v is equal to v minus omega v. That means that you can either count the empty pores or the full pores. So that's exactly similar. And this equation leads, finally, I do not do all the calculations to prove that, to the equation dt of theta is equal to divergence of k, which is a slight modification of k star, of theta, gradient of h, essentially. And generally, we write instead of k of theta as omega is related to theta and p is related to h. We just write simply divergence of k of h grad h. So here is a parabolic equation that you can look at and solve. And of course, you see very quickly that when the medium is full of water, that means that the empty pores are all filled with water, this is zero. And so this parabolic equation degenerates into this elliptic equation. So how can we deal with something which is propagating in time? We cannot under this. So to do that, we have a result that was proven 20 years ago. It's a paper that we published with Christophe Le Potier in 2001. And the proposition is the following. So I take this equation. I assume that theta is a function of h. And this function of h is not a one-to-one function. So that is exactly the problem. So we assume, of course, on a toy model that h of 0 t is equal to an initial value of the quantity of water global in the system. We assume that we want to solve this equation with the boundary condition h of 0t is equal to h0, h of 1t is equal to h1. So the model, it will be for x in one dimension in 0, 1. Remember that if you do not understand the things when the dimension d is 1, there is little hope to understand things when the dimension d is greater than 1. So we always do things with ODEs or PDEs with only t and x as in one dimension because it's the first insight of the problem and the properties of the problem. And if we do not understand that, we cannot go any further. And each time we want to run a numerical code with that, we have no way of seeing if this numerical code, which gives something, because the numerical code is a system of a linear system. In fact, if this numerical code gives something, we do not know if this is related to the solution of the problem. We have good hopes very often, of course, but we have not a way of exactly seeing that. So with that, and the properties, of course, because we want to have something which is current at the beginning, so that means we don't want to have a jump as soon as t is strictly positive. We impose that these are the boundary conditions we impose on the solution of our problem in X, Dirichlet boundary condition, inhomogeneous Dirichlet boundary condition, and we want the initial datum to satisfy this Dirichlet boundary condition. So here is the presentation, and the theorem which was proven was there exists a unique H such that H is in the space W1 infinity of 0, 1 with values in L1 of 0, 1. So enter, sorry. So that means it's for each t we have this almost surely. So that is a proposition that we solved 20 years ago. Okay, you adapt. And I will only give 3 things. First of all, what is the form of theta? Because when you deal with a model, we have to know what is theta. So we have a certain number of laws. So of course, we normalize theta by saying that theta cannot go under a certain value which is called theta residual, as this is written here, and cannot go up, cannot be larger than the saturated theta. So for the moment, let's note that I'm staying with only the porous media equation. The last sentence will not be true anymore. And so, sorry, this is not a large theta, it's a small theta. And here, it's a large theta. So, the small theta is the one which is in the proposition, and the large theta is a reduced one in 0, 1, of course. And the laws can be ln of large theta is equal to A plus B ln psi. And so, of course, I have to say what is psi. Psi is the pressure of air minus the pressure of water. So that is the way water is pushing onto the material, and this is Archimedes' law, in fact. The second law is theta is equal to a power of a value of psi at the power lambda. So this is a law. This one was introduced in 1983. This one is in 1964. And the last one is 1 plus alpha psi at the power n, at the power minus m. And this one is from 1980. And I will give the names because you may encounter them: Williams, Brooks, and Van Genuchen. And which is linked with the uncertainty questions as the following. You see appearing many constants: A, B, lambda, psi EA, alpha, n, m. And in fact, there are no proofs of these laws. So they are phenomenological laws. And so these phenomenological laws come with a mean value of an expandancy and a law for NMN in probabilities. And so when you want to use these laws, you have to remember that numbers n and m are not fixed, and you have to have something which is robust with a small variation of n and m, or, which would be much better, an analytic formula for a solution with n, m, alpha, or lambda and psi EA, and so on. And once you have an analytic formula, that will lead to one of my comments about one of the works I've done in the second model. You can perform a sensitivity analysis if you have analytic formulae. And of course, you have much more analytic formulae in the case of a 1D in space model. That means going to an ODE rather than going to a PDE. And so that's another reason why I advocate the use of ODEs and 1D model at first to understand the use of parameters. So, if someone is interested, I can show. Oui? Yeah.
Yes, it's just a question out of curiosity. Do you have some time regularity results on H?
The time regularity is considered as C1. It can be improved to W1 infinity as well. So that means you can have dt theta in L infinity, but in general it's a classical solution. Once you prove that it's a weak solution, you prove that it's a classical solution. So maybe I can thank Virginie for the introduction, for the next thing that I want to say. So I was saying that for this, for that model, for example, a PhD student of mine, Cécile Baudry, 15 years ago, had some analytic solutions of this equation using that. And so that could be used for the sensitivity analysis. I don't know if it has been done, but that could be a nice thing to do. But as a question of Virginie can lead me to, I can introduce an operator, and which is surprising, it's not a one-to-one operator. So it's the set of U such that U is equal to theta of H0 of x plus V of x. I should be rigorous and say for all x in 0, 1, U of x is equal to theta of H0 of x plus V of x. H0 of x, as everyone can guess, is H0 minus H1 minus H0x. That means the solution which will be the simplest one which satisfies the inhomogeneous boundary conditions. And of course, because it's much safer to deal with homogeneous directly boundary condition, we subtract to any solution of our problem this H0 so that V satisfies zero directly boundary conditions, because it's always safer not to be able to deal with boundary conditions. So, with this U of X, of course, that tells nothing. I have to say, what is V? And in fact, it's a F, rather precisely, such that resist, not a unique, a U, such that, in fact, the value of this is, so I will introduce this notation and explain it afterwards, minus d over dx of k of h0 of x is equal to f. So that means that when I consider all the v which are with a zero directly boundary condition, and when I describe all the sets of these values of depending on v, from this v I compute u by this formula, and I consider the space of all these quantities f as being the set A of u. A of u, that's because I put brackets, it's a set. So it's the non-uniqueness of the problem which is shown in clear light here. And of course, f is a function such that f prime of h is equal of k of h. Because you know, the simplest things which can occur when you deal with an elliptic problem in 1D is that all elliptic problem in 1D up to a composition, it's a second derivative of a function. So every elliptic problem in 1D is the classical operator d minus d square of dx square up this modification. And so the result is the following. In fact, we show that A is an accretive operator. So the details of the proof are long, but I will give you the idea. I fix epsilon strictly positive. I construct U epsilon n of x is equal to I plus epsilon a minus n of theta I of x. Of course, theta I of a is theta of h a, the initial datum. So now, as A is an accretive operator, when epsilon is strictly positive, this operator is a bijective operator, so you can invert it, and solve this. Okay, so now we suppressed the fact that you have infinitely many values in A of u into the fact that there is only one solution of this problem when you add 1 over epsilon I, in fact, to the operator A. Accretive, that means it's monotonous. When you add 1 over epsilon I to this operator, that gives an operator which is the usual cursive one that you can invert with no trouble, no problem. And so from this series of functions, you construct a time-dependent function un of x, which is equal to u 1 over n k of x plus nt minus k, if I do not do any mistake, u 1 over n k plus 1 of x. In fact, you construct a piecewise linear in time solution. There might be a 1 over n over z. Piecewise linear, I think it's that. A piecewise linear solution of the problem. This is un of x and t is equal to un of x k over n, sorry, plus something which will give you the derivative, which is here, that you just constructed. So in fact, this procedure constructs you on a grid the values of the derivative. So this is u1 over n1, u1 over n2, and so on. This is the time steps. You construct a piecewise linear in time solution of the problem, which will be a solution in xt. And from the result of Benillan and Whitbold, you show that this sequence here converges uniformly on 0, 1 for almost every t. And so that gives you a solution of the problem dealing with u, with this u there. So that is the first step. The second step of this procedure is just once you have u, in fact, you can compute u prime, and u prime, which is dtu, it's given by this sequence. So this is dtu. And now, if you take f is equal to dtu, where u is a uniform limit of un, and dtu is computed almost so here, f is in L infinity inter L1. And now, when you look at this problem here, once you give yourself f equal to dtu, this problem is an elliptic problem because large f is elliptic because large f is such that f prime of h is equal to k of h, and I assume, of course, in the Darcy law that k of h is strictly greater than a constant strictly positive, I get a unique v. If I get a unique v, I get a unique theta of h0 of x plus v, and the v, or rather the h0 of x plus v of x, t, almost everywhere, will be a function which is well defined, so uniqueness. And uniqueness, and now if you look at the equation, it's minus f is equal to dtu, otherwise it doesn't work. The u is theta of v plus h0, and you have a unique solution under this procedure of the degenerate parabolic equation, which is right here. The equation is there. And so this procedure, through classical uniqueness of solution and uniform limit for a sequence of accurative operator, give you a unique solution for this degenerate parabolic equation. And once you have a unique solution of this equation, this procedure constructs numerically a unique solution of the unique solution of the problem. And so that means that in this case, the code gives you, with a very tricky way, a unique solution. But the story doesn't stop here for this problem. In fact, for this problem, I will go much higher for the board. Observe, nevertheless, that this problem is quite a tricky problem and a tricky way to treat the porous media. Of course, you take into account the behavior of the medium, but it's quite hard and rather weak as a solution. Oh, sorry, I will write it again. But there is a phenomenon which was induced by numerical observation of Christophe Le Potier that is very interesting. In fact, when you want to solve this problem numerically, so I erased the equation, but you remember it. In fact, you discretize in time. And of course, you have a problem. In the two cases, either you do an explicit Euler or implicit Euler. If you do an explicit Euler, that explodes quickly because the operator on the right-hand side is positive. And if you do an implicit Euler, then the Newton argument to solve the implicit Euler is degenerate as well. You cannot, there is no free lunch in this story. And so Christophe Le Potier did something which was natural from a numerical point of view, adding a pseudo-viscosity in the problem. So the term pseudo-viscosity, normally if I say this in a room, people from CEA in applied math just raise the eyes, because that's the tricks which are used either at DAM, DEN, and every place where you do applied math, from Lascaux and Theodore in the problem. But he explained to me something which was very interesting and very profound. He told me, but this pseudo-viscosity is natural because, in fact, you know, when you put water in a medium, a sponge grows in size. So that means that there is an interaction, a mechanical interaction between the equation of the porous medium and the medium itself. So you have to couple the Darcy law and the porous media equation. So I give back this as the equation, K de H. You have to couple that with the mechanical behavior of the medium. And so a medium is never totally saturated. That means if it has room to enlarge, it will do. And so that's the thing I want to describe quickly. In fact, we will use the following equations. So we have a first equation, which is the fact that the constraint tensor sigma Ig is, of course, given by the classical law of media with G, which is a matrix, alpha and beta, which are constants, with epsilon, the displacement. This is the same epsilon, sorry. You have this behavior of the mechanical constraints. And so that leads to an equation which will be, for the porosity, which is a part of the medium, dt omega is 1/3 of the divergence of a diffusion matrix dt sigma minus a constant times dth. And so the dt omega. What? What is going on? There is a question or something? That's surprising. And so, when you look at this, you can relate theta of h to omega of h, that you can see. But you have an additional term, because here, theta, normally, it can be written s of h omega. And so s of h normally is a nice function, and the only problems come from omega, because omega is fixed to the maximum value of the number of pores. And this omega, of course, you have a dt omega which is proportional to dth, which gives this, and you have dt omega which contains the term depending on sigma. And that's where the things are improving, because this term of dt omega is 0 when h has reached the saturated value of h, but this term continues to increase, because in fact when you want to find sigma in terms of p, of course that is an elliptic equation. So you have, more precisely, epsilon is equal to kt of p, delta Ig, because you invert this problem. So if you have this, P, I recall to you, it's rho GH plus, no, it's rho H plus rho GZ, no, H plus rho GZ, sorry. When you have this, that means that P is H up to a term which is given. And so that means that when you look at the problem where you have dt of theta of H, which is S of H dt omega plus S prime of H omega dth, you have here an additional term elliptic in dth. So in fact, the previous porous medium equation, which is here, which was degenerate because everyone thought that this term was zero when H was constant as well as this one, in fact, is not zero because of this additional term coming from the elliptic equation of the behavior of the material. And so the degenerate porous medium equation becomes a non-degenerate parabolic problem. Every code will solve that directly. So that was the thing I wanted to show, is that you have one technique, which is a very, very tricky technique. This very tricky technique corresponds to an artificial viscosity that you add to the problem. But this artificial viscosity that you add to the problem has a physical meaning and comes from the behavior of the material. And in fact, Christophe Le Potier, when he did his numerical experiments and results, he added an artificial viscosity, a pseudo-viscosity, which was related to the deformation of the medium. And he said that the good way of choosing the artificial viscosity was this one. And of course, I was intrigued, and he told me, but that's the behavior of the material. And then we did that and observed that that was really, when you couple the behavior of the porous media equation, which need to have an accretive operator and to get a set of all possible solutions, because when you have a function which is on a saturated zone, you can change the value of the function at any time. When you couple this with the behavior of the material, you have a much more regular problem and existence and uniqueness of the solution of the coupled problem. So that is the first thing I wanted to present as a problem where you have a coupled model and coupling models instead of coupling codes. But it's not too much characteristic of that. The second theme I want to describe, so if you allow me till 10, is it okay? It will be 1 hour and 15 minutes. Do you agree? The second model, I will begin by a small cartoon. And I like this, it's funny, and so this is trees and two buildings in one place, which is situated where Osiris was in the past. And you have two buildings. One of them, let's say, is the neutronics building. The other one is the thermohydraulics building. And both buildings have been working, one of them since 50 years, the other one since 30 years, on very accurate and precise numerical codes for solving two different problems. But these two different problems, in fact, let's say 25 years ago, people realized that the two different problems were interacting and could not be solved separately, had to be solved iteratively. And generally, when I describe that outside, I said that there is a building of neutronics. So the neutronics compute something which is called phi, and to simplify, phi is the density of neutrons in the nuclear core. And once they have done this very precise computation, there is an intern which takes, this was 25 years ago for saying that, which takes the list of data and just climbs down the stairs, crosses the courtyard, and climbs up the other stairs to give the list of datum of the density on a file or on a paper. That was 25 or 30 years ago. That was still papers with data to the thermohydraulics building. And this thermohydraulics buildings uses that as boundary data. That means the density of neutrons gives you the transfer of heat, and this transfer of heat is a source term for the equations for the neutronics, for the hydrodynamics. And the hydrodynamics and thermics gives you a pattern of temperature in the fluid, or rather, a pattern of enthalpy. And after they run their computation, they give back the pattern of enthalpy as a function of space, and another intern from the other building gets down the stairs, crosses the courtyard, gets up, and gives the pattern of enthalpy or temperature to the neutronics building. And the neutronics building just has an equation which writes like that: d phi over dz plus sigma a of z phi is equal to nu sigma f of h over k efficient phi, where the quantities d of z, sigma a of z, and sigma f of z, which will be, I suppose, described more precisely by François in his talk. When are you talking? Friday? Friday morning. Will be described. It's a diffusion constant for a problem which is an approximation of the transport of neutrons. This is an absorption function which describes how many neutrons are absorbed in every position of the problem. And this is a fission constant which gives how many neutrons are produced. And in fact, the idea, of course, when a nuclear core wants to work correctly, is that you have as many neutrons as absorbed as product. So you want to have a problem where Kf is the closest you want from 1. And so they did. Yes, Olga? I ask. Yes, I asked for tell. Nobody complained, so I can do 10 minutes, no problem. No problem. But you should have told me at the... Okay, so the closest of Kf being 1 is this. So this d of z is computed using the function a for g, which is the enthalpy in every point of the domain. I take z as 1d following my previous argument. But in reality, the problem is not these two ones, but is a problem which is coupled. So that means, of course, you see how it's coupled by this small idea of someone climbing up and down. And the real problem is this one, d over dz of d of h d phi over dz plus sigma a of h phi is equal to nu sigma f over k f phi, where sigma f also depends on h. Phi of 0 is equal to phi of L is equal to 0. That means that you do not have neutrons which go outside the domain. And H prime it's a simplification, is equal to C phi. And H prime of it, it's dH over dz when you want to find a stationary solution. And you have also, you know that the enthalpy or the temperature on one side of the problem, which is 0, is the entrance enthalpy, and H of L is equal to HS given. And you have also additional conditions, which are phi positive, and the integral from 0 to L of phi dz is equal to 1. Why these two conditions are relevant is that the first one, it's because you could not have a negative density of neutrons, and the second one, it's a probability density. So, of course, the integral is. So that gives you exactly C. C is necessarily equal to the fact that when you integrate from 0 to L, you find HS minus H. And so now, instead of having two coupled problems, you have only one system of ODEs in this case. And in the last 5 minutes, I will describe the way we have to compute the solution. And I will say the unique solution of this problem with a much more regular problem. In fact, we resume to the finding of Kf as a solution of an equation, not an ODE, nothing more, an equation. So, to simplify, d of h is equal to d, sigma a of h is equal, no, sigma of h is given. And I will solve the system of ODEs. Of course, you will notice that the system of ODEs, it's a system of order 3. You have two derivatives on the first equation, one derivative on the second one, and you have 4 conditions. So that's too much. So that means that the value of Kf is determined by this problem. When you look at that from only the Newtonics point of view, Kf is considered as an eigenvalue of an operator. So you have infinitely many of them. When you look at the coupled problem, Kf is unique. So I put 1 over Kf to simplify the notation is equal to lambda. And I will solve the equation. It will be 2 equations. So minus d over dz of d of h d square h over dz square. So I assume d because I replace phi by 1 over c dh over dz plus sigma a of h dh over dz is equal to lambda nu sigma f of h dh over dz. So that's a totally integrable equation because everything has a derivative. So I will note sigma tilde a of h such that sigma tilde a prime is equal to sigma a. Nu sigma f tilde a prime of h is equal to nu sigma f of h. And so I get integrating minus d h second, I forget it's d over dz, plus sigma tilde a of h is equal to lambda nu sigma tilde f of h plus the first constant of integration. I multiply by h prime plus sigma tilde a of h prime is equal to lambda nu sigma tilde f of h prime plus sigma 0 h prime. Fine, we can integrate again. And we can integrate again, do it, minus d h prime square over 2, plus something that I will call by commodity u of h is equal to lambda v of h plus sigma 0 h plus sigma 1, C01 h plus C1. I did two integrations of exact integrable functions. I have two constants of integration, and you can guess that these two constants of integration will be given by h of 0 and h of L. So, in fact, you deal with all those things so that h0 and h of L gives C0 is equal to C1 is equal to 0. And now I have the ODE. H prime is equal to 2 over 2 square root of d, sorry. Yes, square root of d over square root of 2 u of h minus lambda v of h. So that is the ODE. We resume to an ODE of order 1 with a parameter. And finally, I will give the equation that you have to solve. The equation that you have to solve, it's integral L is equal to the integral from HE to HS of square root of D over square root of 2 u of h minus u lambda v of h dh. So everything is given here except lambda. Lambda is solution of this equation. You have a unique lambda solution of this equation. Once you have this unique lambda solution of this equation, you solve the equation, and then you have an exact solution of all the coupled problem. Why did we suppress the fact that we could have infinitely many eigenvalues to the problem up there? It's because hidden there is the hypothesis that h prime is always positive and does not vanish, which is phi positive. And so, in fact, this gives a unique solution of the problem with phi positive. And you resume with this equation. And while in Montreal this year, François Dubois just gave a method, a numerical method that can be used directly using a Crank-Nichols scheme to solve this equation. And after that, if you are interested, you have plenty of small models using special functions that will give analytic solutions of this problem and an analytic value of lambda. And so once you have an analytic value of lambda, you can do uncertainty analysis. So I will stop there, and I will thank you for your attention, and thank you for Olga, Virginie, Tommaso, Fabio, and so on, for the proposal of giving a talk. And that's so nice to give a talk with real figures behind you, and with a chalk and something like that. And thank you for all the organizers, also for the organization. It's lots of fun.
Thanks a lot, Olivier. Thanks a lot for the nice talk.